Oh yeah. An actual break. This is my information from my first one. That was a lot. Oh, that's already in there? No, I read it. Yeah, this is my first one. I'm trying to do it. Because like there's like a lot of sources that are like, oh, this year I sent this.
Person in class.
Craziness. Did you go to spin class? No, it's not that. Apparently it's really hard. I feel like it's knowledge. Yeah, but I have no knowledge. Why? Because I know nothing. That is all. I'm not that old though.
Good call.
I wasn't planning on taking them. Jesus.
Welcome.
Yeah.
We have 3 today. New low? Well, it's too bad. We're doing some demos today too, so it's a good day to be here live. Seeing people starting to come in online. Good to see. If the audio is bad, please let me know. Although it's looking like the levels are okay at this point. I can usually tell from my end if it's going to be good or bad for you. Great, thanks Jasmine. New unit today. We're going to be looking at air pollution. And a couple of things maybe just to clear up with everybody. First, we have the next set of, what do we call them? Unit quiz or unit assignment went up this morning. And this will be on this upcoming unit, which is going to be on air pollution. So please check that out. I thought I posted the lecture slides already, but I just checked now and I didn't apparently. So these slides will go up before too long. Obviously not like during this class, but when I get some time after class. They are up?
Yeah.
Oh, maybe I just didn't refresh my screen then. Okay, I thought I put them up and then I couldn't find them. So great, thanks. Glad I'm organized and clear here. Okay, so we are starting a new unit today. Just a reminder for the assignment 1. Due date for that, I believe, is 10 minutes ago next week, right? 1 week from today at 2:20. So please make sure that you have that done. And if you're not familiar with submitting assignments online through Acorn, you might want to give yourself a bit of time. I think it's straightforward. I've never done it myself, so I don't even know what it's involved. But in past years, no one ever seems to really have any trouble doing that. Just one thing I really want to reiterate, 2 things with that assignment. One is make sure it's 1 page. Everything's got to fit on 1 page, including the references, including your title, including anything else you want on there. No appendixes, nothing like that. Second thing is make sure when you upload it, it's either a Word document or a PDF. Those are the only two acceptable formats. No RTFs or whatever other word processor you might be using. Don't put an image file. Some people sometimes put like a JPEG of their whole thing. I don't want that either. And that's because all of these go through Turnitin, and in order to properly be processed, we need PDF or Word documents. So just be aware that that is the case. All right, so we are starting a new unit, and the unit is going to be on air pollution, which we'll get through. I mean, there's lots of slides, but I think there's lots that I've X'd out too, so it'll go a little quicker than it might appear. This is going to be our first of a few units which are going to focus on different aspects of air pollution. The first one is just going to be sort of your garden variety air pollution, the different pollutants that end up in air from manufacturing, from driving your car, from all these sorts of things. The second one we're going to look at, what order are we doing these in? We're going to look at ozone, ground level ozone layer, depletion of the ozone layer a little bit. And the third one is going to be a little bit on global warming, on carbon dioxide, other greenhouse gases, and a little bit about the chemistry behind that. So hopefully those 3 units go pretty quick, and they're all kind of thematically linked at least. So I guess to begin with, we want to look at this planet that we all live on, which is Earth, and consider our atmosphere itself. And you can actually, if you look very closely at the edges of the Earth in this photograph, you can kind of see like a little narrow, hazy outline. If you're looking at it on the projector, everything looks hazy, but you know, if you look at the picture, bit of a hazy outline. That's our atmosphere, which we think is very thick. If you look up and you see a plane way up there, like it seems like it's a really thick layer of air, but compared to the size of the planet, it's actually extremely thin. This is a closer up image, and you can see there kind of the haziness and how it looks like it kind of fades out. Like it's very strong. That's reflecting light, which is why you see it. Particles in the atmosphere reflecting light. So it's not like a layer where there's a sudden stop. It just sort of gradually fades out as it goes up. And I've often seen it's said that the atmosphere of our planet is a little bit like the skin of an apple. So like the thickness of the skin compared to the whole apple is, you know, within a few orders of magnitude at least. Like it's roughly how you can think about the thickness of our atmosphere. So yeah, it is big from our standpoint, but not as big as we think. The atmosphere is broken up into different layers, and the layers, the division between the layers is actually depending on the temperature. So what we find is as you go up in altitude, the temperature drops. So if you climb a mountain, that's why mountains have snowy peaks, because it's colder up top. The atmospheric temperature goes down the higher up you go, up to a certain point. And once you hit a point around 10 kilometers, that changes, and if you go higher than that, the temperature of the atmosphere actually goes up again. It starts to increase. And that cutoff between decreasing and increasing is sort of the boundary of the first 2 layers. So the layer that's closest to the Earth, and the one that we are most concerned with, because that's the layer we live in, is called the troposphere. That means like the layer of the atmosphere where all the life is. So other than, I guess, people on an International Space Station, all life that we're aware of is in the troposphere right now. Stratosphere is the next layer up. It's much thicker in terms of, like, you know, the altitude limits. You know, there's more in there, but in terms of the amount of gas, the density of gas, the air pressure, it's much, much lower in the stratosphere than it is here in the troposphere. So it's starting to fade out already, and we would notice greatly reduced air pressure. And then above that, you see there's the mesosphere, thermosphere, exosphere. We're going to concern ourselves mostly with the bottom 2 layers. This is basically the layers where essentially all human activity takes place. All right, so what we want to talk about at first is we want to make very clear what the chemistry of this atmosphere is and these layers and what that means for us. So it was way back when, I think we talked about Lavoisier. One thing Lavoisier did, in addition to Law of Conservation of Mass and his book called Elements, one of the things he did was he discovered that air was 80% nitrogen. And he did this by taking air, reacting it with mercury actually, and pulling out the oxygen. And he found the remaining fraction was nitrogen. And he thought it was 80%. We now know it's like 78%. So he was pretty close with his measurements, which is pretty good for, what, 250 years ago? And it was, who was the guy's name? He was a British scientist shortly after, found that essentially the rest of the gas in our atmosphere is oxygen, around 21%. There's many other gases that are in our atmosphere as well. In addition to oxygen and nitrogen, they make up, in total, only 1%. So if you take that 1% and kind of further subdivide it, the major gas in that remaining 1% is argon, which makes up 0.93%, which is most of that remaining 1%. And then CO2 is the next smallest one. CO2 is 0.04%. So carbon dioxide we hear about all the time. You know, it's the one that's always talked about in terms of global warming. It's what plants need to photosynthesize. It's what we give off when we undergo cellular respiration. So you hear about carbon dioxide a lot, but in terms of percentage of our atmosphere, it's actually very low and, you know, small but mighty. It's a small fraction, but a very important fraction of the air that we have. Very small amounts of these other things like neon, methane, helium, hydrogen, krypton. About 120 years ago is when a lot of those noble gases were extracted from our air. They're all present in the air we're breathing right now, just in very, very tiny amounts. Poor Food Babe, we're bringing her back up again. For a time, at least, on her website, there was a section on travel advice. And this is her travel advice if you're going on a plane. The air you're breathing on an airplane is recycled from directly outside your window. That means you are breathing everything that the airplanes gives off and is flying through. The air that is pumped in isn't pure oxygen either. It's mixed with nitrogen, sometimes almost at 50%. To pump a greater amount of oxygen in costs money in terms of fuel, and airlines know this. The nitrogen may affect times and dosages of medications, make you feel bloated, etc., etc. So I don't know where she got this from, or if she just completely made it up, because it's, you know, it's crazy. The air we breathe is not 100% oxygen. It's not pure oxygen. The idea that nitrogen make up almost 50%, well, it makes up way more than that. It makes up almost 80% of the air that we're breathing right now. By the way, this is all assuming the air is dry, because air can have different amounts of water in it as well, up to 5%, and that's usually the relative humidity. So assuming the relative humidity is 0, that's where we get these numbers for all the other things. Those numbers will shrink slightly as we add water to the air. So yeah, we actually can't breathe, or at least healthfully breathe, air that contains greater than 20% oxygen, except under maybe very specialized circumstances. So there's an air mixture called nitrox, which has an elevated percentage. In this example here, you see 36% oxygen, which is a little more than double. And this is the kind of gas you would use if you went scuba diving, that would be in your tank, because obviously you want to minimize the amount of the size of the gas tank you have to carry around. And you can use this gas mixture safely for short periods of time, but requires training. Okay, so generally speaking, you don't want to be breathing in more oxygen. And I guess in the hospital too, they'll give you a feed of oxygen. That's not pure oxygen either, but it's typically that's if your respiration is compromised and you're not extracting the full amount of oxygen that you should be, you can get put on oxygen that way too. Okay, so one thing I wanted to mention, we talked about the gases that are in air: oxygen, nitrogen, what else is there? Helium, a little bit, methane, carbon dioxide, argon, all these other things. I just want to distinguish now which of those gas particles, if you went down to the atomic level, are considered molecules and which are considered atoms. So if you have a molecule, that means that there's more than one atom that are bonded to each other. They're stuck together through chemical bonds, which are very difficult to break. At room temperature, certainly, generally speaking, they're not breaking. So oxygen is made up of 2 oxygen atoms to make an oxygen molecule. Nitrogen is made of 2 nitrogen atoms to make a nitrogen molecule. Helium is just a single atom all by itself. It does not form bonds. Same with argon, which is present in much greater amounts than helium. So these gas particles that we're dealing with here are a mix of molecules and pure elements, pure atoms that are all mixed together in there. So these little particles are in the air, they're flying around, they're colliding with each other, they're bumping into each other, bumping into the walls, everything. But that doesn't cause these molecules to break into pieces, unless you really heat them up. All right, so the difference between the states of matter, gases, liquids, and solids, are that solids have all of the particles in close contact with each other, and they're in a very regular arrangement. So they're kind of stacked and they're in one place. They're vibrating, they can jiggle around a little bit, but they're not flowing, right? They can't move past one another. A liquid has them, again, still in contact with each other. So generally liquids are roughly the same density as solids. They're usually a little bit less. They're in contact, but they can kind of roll over each other. So you can think of a liquid as being a little bit like a bucket of sand, where if you sort of slosh it around, the sand will flow and move, or each little grain is like a liquid particle. They'll stay together and it'll flow, but it's not very hard for one grain to move relative to another one. My mic just went a bit quiet. Is it too quiet? I saw it kind of peaking here, so I just turned it down just a little bit. I'll just turn it up just a touch. I see when it starts to go in the red, so hopefully that's maybe a bit better. Gas particles are very far apart from each other most of the time. On average, gas molecules are very small relative to the space between two particles. So they can travel quite a distance on the molecular scale before they'll collide with something else. And they're flying around, moving a constantly they're in motion. They're not stopped. They'll bang against the wall, bang against each other, and they'll undergo all these collisions constantly. And we say these collisions are perfectly elastic, which means you think of a ball that's like perfectly elastic that'll continually bounce forever. That's what these gas particles are doing. They never run out of energy, and then they never will settle. Okay, first question in our new unit. What gas is the third most abundant in air on Earth? Oxygen, CO2, argon, or nitrogen? Well, we know number 1 is nitrogen, making up 78%. Number 2 is oxygen, making up 21%. Then we have CO2 and argon. Argon is number 3. It's like 0.93%, and CO2 is roughly 0.04%. Great. Which of the following is not one of the 4 states of matter? Plasma, liquid, gas, solid, air. And I think we talked about this one in previous units. Plasma, I didn't mention yet. Plasma is just a gas where the particles are charged. So the answer here is air. All right, so some of the earliest chemistry that was done when you could kind of see a distinction between alchemy and chemistry, and the real distinction there was application of the scientific method, which means people did experiments where they varied one variable at a time. They made very careful measurements. They looked at things objectively, and they, of course, wrote down their work and shared it with others. All these things that we associated with the scientific method. A lot of this was done first on gases, and the reason for that was because the kind of equipment you needed to do these sorts of measurements was very simple. People were quite good at making glassware by heating glass up, and it was sort of a well-developed art at that point in time. And so they could make the apparatus quite easily that they needed to do these sorts of measurements on gases. They had manometers, which are glass apparati, is the plural, with mercury in them to measure pressures and all these sorts of things, so they could make these kinds of measurements. So this preceded most of the chemistry, even that we talked about in our history of chemistry. Of course, it came after fire, but you know, some of the more things after that. So one of the first people on board was a scientist with the last name Charles, and there's a law named after him, Charles' Law. And what he did is he looked at gases and how the volume of the gas would change if you heated it up or cooled it down. And what he found was that there was a straight line. Basically, the volume of a gas is just some constant multiplied by the absolute temperature. And what he actually did is he followed that straight line backwards to zero volume. So you can see the dotted line here. He made a bunch of measurements at different temperatures where he knew what the temperature was, drew that line backwards, and noticed that no matter what sample of gas he was working with, didn't matter what the gas was, it didn't matter the initial pressure or the initial whatever, they always backed to the same exact point. And what he said was, this is the temperature, this must be the temperature, the farthest left point here. If I can make, yeah, I can make my little thing glow here. This little point right here, where they all fall back to, is what he called absolute zero. He said this is the lowest temperature you can get, because if you went lower than that, it wouldn't make sense, because you can't have the volume of the gas go below zero. It can take up no space, or it can take up some space. So this is a very interesting thing. First of all, that volume increases with temperature, and second of all, that you can extrapolate backwards these lines to determine or estimate at least what absolute zero is. So pretty early on, they had an idea of this lowest possible temperature, which is called absolute zero. Now, this, I guess, has some implications for our real lives. This is the whole idea behind a hot air balloon, that if you take a hot air balloon and you turn the flame on, torch on, I don't even know how they heat them in a modern one, that will warm up the air, which will cause the air to expand, and it'll inflate the balloon. So you need the balloon inflated at first. And because it's expanded, it's actually lower density, which causes the whole thing to float upwards. And that's, so the air needs to be hot in order for that to be the case. I have a friend as well, and she grew up in northern Saskatchewan, where it can get very cold in the winter. It's a little chilly out here today, but nothing too bad. They would get minus 40, or colder. And what would happen is, think of the tires of your car. The tires of your car are a sample of gas in a somewhat flexible container. And if you cool them down, the volume will go down as well. And so what happens to tires at very cold temperatures like that is they go like semi-flat. And not only do they go semi-flat, the bottom of the tire kind of becomes flat. It's not round anymore. And rubber, as we'll see in just in a few minutes, when it gets cold, gets hard. It's not flexible anymore. And so what happens in the wintertime, you should say, you get and you drive your car, and it would be like ka-chunk, ka-chunk, ka-chunk as you're driving and the wheel isn't round. And then eventually, after a kilometer or so, the wheels warm up, and then they flex, and then they kind of inflate a little bit, and it's normal driving again. So there's Charles' Law for you. Boyle was another one. He was looking at the relationship between pressure and volume, and he found that the volume, if you double the pressure, external pressure on a sample of gas, the volume will get cut in exactly half. So there's a very close mathematical relationship. Just notice that these laws, Charles' Law and Boyle's Law, are great examples of scientific laws because they are relationships that are expressed in a simple mathematical equation with no explanation as to why this relationship exists. That's what a law is. That's our definition when we started this course. Okay, so what I brought today was actually a couple of pieces of gear to show you some of these features of gases and how those gases can change their properties when we change their temperature. So I'm just going to slide over here to my table. All right, so can you see you can see my head in the picture too. Okay, so what I have are first of all, some balloons, which I'm going to just push off to the side. And I have this big styrofoam container. Styrofoam is great for keeping things cold that are supposed to be cold. This is, it's sold as a cooler, so you can put your cold drinks and ice in here and it'll keep it cold. I'm going to be using it for liquid nitrogen. And so I have a container of that right here. And liquid nitrogen, you can see, is in a special container. This container is called a dewar. And essentially what this is just like a high-end thermos. It's stainless steel on the outside, and then there's a second inner container, which is also stainless steel, and there's a vacuum in between the two layers of stainless steel. So the idea is that there should be no heat that goes into the container or back out of the container. And so it's meant to hold, well, I guess you could put your coffee in here, like a big thing of coffee, and it would stay hot for a very long time. Or you can put very cold things, which is what, of course, it's designed for. So what is in here is nitrogen gas that has been cooled down and condensed into a liquid. So most gases, we know if you cool them down to a certain point, they'll eventually become a liquid. That temperature for liquid nitrogen turns out to be negative 196 degrees Celsius, which is, I believe, 77 degrees Kelvin, which is the absolute temperature scale. If you start as the lowest possible temperature is 0 degrees, 77 degrees above that is what this nitrogen is at. So that's cold enough. Of course, this is much colder than you'd ever experience outside. I think I read in the news this past week that some place up north experienced the coldest recorded temperature ever recorded. And it was like, I don't know what it was. It had wind chill included. So it was like minus 60 something or minus 70 or something like that. This is still way, way colder than that. It's interesting actually because if you get to a temperature of about minus 80, minus 78 is the point at which carbon dioxide will deposit. It'll turn into a solid. And so I guess if it got colder than minus 78, it could start snowing carbon dioxide, which would be kind of cool. All right, so what we're going to do is just take our liquid nitrogen and pour some in here. And if you see it as it pours out, it looks kind of just like water. And maybe you can hear that. I don't know if you're online, if you can hear that okay or not. You can hear my voice, can you, if you're online? I'm sure it'll work. Okay, so the first thing we're going to do, remember we said how if you have car tires that are very cold, the rubber will become solid. I'm going to just demonstrate that using just a piece of rubber tubing. And so you see it's very flexible, it's stretchy, and it's got a hole in the middle so you can pump air or whatever you want through it. It's got a thick wall on it. It's designed for putting things under vacuum. And we can kind of just put that in the liquid nitrogen. And you can see every once in a while it'll spit a little bit out. Great. So that's making it nice and cold. And so you see this, and it becomes very hard and brittle. So I don't know if there's anything, usually I try to smash this off something, but everything I see around me is like more brittle than this right now. So I'm going to smash it and not the actual piece. You might notice as well it's turning white. And the reason it's turning white is just because water that's in our air right now is basically turning into frost. It's coming into contact with the outside of the rubber and it's freezing. As soon as it hits it, turns into a solid, and you can kind of see a little bit of, it almost looks like steam or smoke coming off. That's fog, basically. It's water that's condensing when it gets near from the air And if it gets too close, it freezes and it builds up that white kind of layer we have there. Now, one thing that I can show you is that, yeah, it's holding it in pretty good. When you have a substance that's in a liquid state, if you convert it from a liquid state into a gas phase state, what happens is the volume dramatically increases. So gases take up way more space for the same amount of material than you do when you have a liquid. And I'll show you that just with a little bottle here. I'm going to just grab a sample of our liquid nitrogen. There. So it looks kind of like water, except it's a lot colder than water. And if you look at it, it's boiling. And that's because it's, even though it's really cold right now, it's at its boiling point. And I'm just going to take this balloon and put it over the top. So what you can see right away is that as that absorbs heat from the surroundings, it's boiling, it's turning into a gas, and there's probably, I don't know, maybe, I don't know how clear that is in the video, but there's maybe an inch in the bottom of this container. And you can see already how full the balloon has gotten, and it's like barely any of it has evaporated. And that's true with every liquid. Every liquid, when you convert it from a liquid into a gas, the volume that it takes up increases by a dramatic amount. So let that sit there. One other thing I'm going to show you too, just to show you that this is like any other liquid that is boiling, is I'm going to have a kettle. And this is like those kettles that have the whistle. So when the water starts to boil, turns to steam, and the steam shoots out through the front, which makes the whistle blow. So what I'm going to do is so you can see that, see it shooting at the end, and then it whistles. So you can see this is like a boiling liquid. I don't know how loud this is online. So this is just a boiling liquid, just like water, right? And what's actually interesting is if you let this sit for just a minute, and I don't know again if this is going to be clear at all on the camera, but what will start to happen, it's starting to happen already, on the sides of this, first of all, it will turn white, just like the rubber hose did, because when water comes into contact with it, it starts to condense. But you might see that it's starting to drip. Can you see that dripping off? I don't know if the camera, if that catches it. I'm going to come closer to the camera. And so yeah, you can see a bit of liquid dripping off of this. That is actually liquid air. So what's happening is the bottom of this is now so cold, and it looks like it's really wet, it's really dripping here. It's so cold that when the air is coming into contact, it's turning into a liquid as well. So this is a mixture, I guess, of liquid nitrogen and liquid oxygen, and when it comes off into my hand, it kind of just poofs away, like it doesn't make my hand wet. I'm going to show that here. So yeah, my hand is perfectly dry. Charles' law. Remember Charles' law? We said that in Charles' law that if you cool down a gas, its volume decreases. So why don't we try that? We have a couple of balloons here. I see 3. I think I had one's. Oh yeah, there it is. That one fell. So let's put that in here. Put another one in here. Shrink them right up. Shove them down so they're fully immersed. And you can hear them, they're kind of crunchy. Yeah. That was nice and loud, wasn't it? We'll see if upstairs people come running. Okay, so we have our 4 balloons that are in here now. And these 4 balloons look a lot different from when I first put them in. So it looks totally deflated. And then if you kind of just bounce it around a little bit and warm it back up, you get your balloon back. Let me do one more of those a little closer to the camera. You can see it's all kind of deflated and crinkly looking. Looks kind of slowly warms up and becomes our balloon again. Just in case that wasn't super clear, I'm going to try the other camera just to make sure. There goes the balloon. You can see it pretty well. Great. There we go. Dripping liquid nitrogen all over my computer. You can see it's all kind of crunched up. And then warm it up a little bit. Totally reinflates. It's all good. Great. So we're learning all kinds today, aren't we? Let's take out this last one. Now, one actually interesting thing about liquid nitrogen is you can pour it on your hand, and like whenever I'm doing demos with liquid nitrogen to little kids, often I get the question like, "Stick your hand in it." What you know? What happens if you stick your hand in it? And yeah, your hand is mostly water. If you put your hand in here, it would freeze it solid, and like more solid than ice. And if you like slap the table with a frozen hand like that, your hand would shatter and just go all over the room. I don't know if the bones would probably go with it, so you probably wouldn't be left with just like a skeleton hand. You just have a stump, frozen stump. Although it was for a bunch of grade 2s. One year I had rubber gloves on, and I pulled my finger down and put a hot dog, and I stuck that in and I froze it, and then it went like, psh, and it shattered all over the place, and they thought my finger exploded, but it was not my finger. But if you have this stuff and you hold your hand out, you can pour it on your hand instantaneously. And because this is so hot, or so cold, it's almost like if you have like a really hot frying pan and you pour water on the frying pan, the water kind of like balls up and kind of moves over the surface like that. It doesn't like just sit there and cool it off. It's boiling as it's touching the surface. So my hand is like extremely hot compared to the temperature of the liquid nitrogen. So of course when I pour it, does anyone want to come up and try? What's that? You're good? It's not going to hurt, no. I just did it myself 3 times.
You can go first.
So just make sure your hand is wide. We're going to just...
Ooh, that's cool. Wait, do I put it like towards the...
Yeah, like don't cup it. That's all I ask.
That's so cool.
Yeah, because if you cup it, it'll sit there and then it'll freeze you, right? Because it's yeah.
Oh, I was like, why is this so cool? Because my bracelet.
So I don't know if you're going to be able to see this, but it's going all over my pants. Yeah, there you go, folks. So that's liquid nitrogen. We can dump. I've actually ruined the floor before in 2 classrooms, actually. Don't tell anybody, even though this is being recorded online. But in the BAC, the classroom I was in once, the floor was carpeted, but the carpet was made out of these square tiles, and they were like rubber backed. So they kind of went in one at a time, little squares, and the rubber froze and became brittle, and they curled up. And it caused all the glue that was holding them down to like give way. So they all came loose. So it didn't really ruin the floor. All it did is made it so that I had to glue them back down again. Yeah, so what's this chem demo if something doesn't go wrong now and then? All right, we got some comments online I want to get to. What, did it ruin the floor a little bit here? Shh. Jasmine says, I find it hard to understand at first when I learned that absolute zero means none of something. Yes, the numerical value is not necessarily zero. So yeah, absolute zero, negative 273 degrees Celsius, 263 degrees Celsius. No, 73. 73, yeah. So yeah, it means that's the lowest possible temperature you can have. It doesn't mean that there's no molecular motion. There is still molecular motion at 0 degrees Kelvin, but you can't get less motion than what you get at 0. Could you drink liquid nitrogen on a hot summer day to cool off, or is that unsafe? Yeah, that's not recommended. In fact, somebody died doing that. There was a bar that was selling drinks that had a layer of liquid nitrogen on the top, and it was just for the reason the liquid nitrogen was there was just to make it look cool, and it bubbled and it gave off gas and it probably had some sound, it fizzed a little bit, all these sorts of things. And what ended up happening was this person shot the whole glass, which actually the problem wasn't that it froze them on the way down. The problem is when it got to the stomach, it did what our balloon did, right, on the bottle. Where the balloon was her stomach, it turned into a gas very suddenly, it expanded, and it ruptured her stomach. And rupturing your stomach is not a good thing to have happen to you. There was another story where I think it was an event at a resort in Mexico, trying to remember the details, and it was sponsored by Red Bull. And it was one of these like, kind of like a big party for spring break, or one of these kinds of things. And so they had a bunch of people in this pool, and they decided to pour in about like 10 liters of liquid nitrogen into the pool that everyone was swimming in. And that looks very spectacular. You get lots of smoke and all that. And again, the danger wasn't that anyone froze by touching it or came into contact with it. The problem is that it all turned into a gas, and it like filled up, it displaced all the oxygen, and everyone in the pool weren't able to breathe. And a whole bunch of people ended up in the hospital. I don't think anyone died. I think they kind of recognized pretty quick what happened. And because the air was cold, the nitrogen air was cold, it sat on the bottom. It was a little bit more dense than the air. So yeah, that's not so good. So certainly you have to respect it. Like every chemical, there's pros and cons. You have to, yeah, you guys know what I'm gonna say. Yeah, for when I dump the nitrogen. So I can't do it here, but what is also pretty spectacular is if you have a container full of hot soapy water and you pour liquid nitrogen in it, suddenly turns into a gas, but it turns into like a bubbly foam, and it all foams up and makes like a great big mess, which is certainly a lot of fun, but too messy for right here, I think. I don't think they'd appreciate that. Cool. So yeah, well, you poor people online, you didn't get to experience this firsthand. Come by sometime and I'll pour liquid nitrogen on you a different time. Okay, so we have some laws. I said this already, but water is present in our air anywhere between 0 and 5%. And 5% would correspond to 100% relative humidity. 0 would be very dry air. So if we went to the desert, it's closer to 0. Davy, remember Humphrey Davy, showed us that water was 2 parts hydrogen to 1 part oxygen by volume, or by number of atoms. And we understand now very well what the actual structure of water is. It looks like this kind of picture you have here. It looks like kind of like a Mickey Mouse head, upside down, I guess, in this picture, but kind of like the face with the 2 ears. And the big red one in the middle is the oxygen, and the 2 small ones are hydrogens. Hydrogens are a lot smaller than oxygen. And they have a bond angle, like if you took the centers of those 3 circles and connected them, you would have like a bent line, and the angle is 104.5 degrees. We know this very well. Every water molecule in the world has the same structure. So in terms of atomic structure, you remember our historical walk through the world of chemistry, and J.J. Thomson, what was it, 1897, I think, discovered the electron. 1911, Rutherford discovered the nucleus, which has the protons and neutrons in it. So for about the last 100 years, we've had a pretty good understanding of the structure of an atom, where there's the nucleus with the protons and neutrons, and the electrons are surrounding it. Mendeleev, slightly before we knew that the structure existed, arranged all the elements in the periodic table, and he arranged them according to mass, which corresponds to the number of protons and neutrons that are in the molecule, or in the atom. So shortly after this, another famous chemist, G.N. Lewis, came along, and he proposed in 1918 that in molecules, these bonds that hold atoms together are the result of electron pairs that are held by 2 atoms simultaneously. So if you look at a hydrogen atom will have 1 proton in the nucleus and 1 electron surrounding it, and those charges balance each other, and the atom overall is neutral. What will happen, though, is that that single electron in the hydrogen atom will combine with a single electron in another atom to make a pair. And for reasons that delve into quantum mechanics, pairs of electrons are a more stable arrangement than having them all by themselves. So these 2 electrons are sort of simultaneously attracted to the 2 nuclei, and they act as sort of like a glue almost that bonds these 2 things together. And these are called covalent bonds. Okay, there's other ways that particles can be attracted to other particles. Large-scale particles, like particles of dust, can be attracted by like static electricity. In many compounds, ionic compounds, you have oppositely charged ions that can attract each other because of their charge. But in molecules like hydrogen and like most organic compounds, it's covalent bonds that are holding the atoms together. So Lewis is the one who came up with this model. He shortly died after that. He died in his own lab. I think it's debatable whether or not it's considered a suicide, but I don't think it was. What he was doing is he was doing a chemical reaction using as a solvent hydrogen cyanide. And hydrogen cyanide is what we call a volatile liquid. Volatile means it easily evaporates. It goes into the gas phase very, very easily. And you have to be very careful if you're working with this. In fact, I wouldn't work with it just because the risk benefit is just not there. But if you were, you'd definitely want to be in a fume hood where you're protected from any of the vapors that could be coming off of something like that. He was doing a reaction with that as a solvent, and apparently he was doing it well into the evening. And the next morning, his graduate student came to the lab and saw him collapse on the floor. He knew the reaction he was doing. There was no fume hoods at that point in time. And he saw his reaction flask broken on the bench. So cyanide is bad enough to eat it, but hydrogen cyanide basically turns cyanide into a gas that you can breathe in and very quickly absorb it and die. So he did die of cyanide poisoning by breathing this stuff in. His graduate student was smart. He kind of knew what had happened. And what he did right away, because there's no ventilation to speak of, is he plugged his nose, held his breath, opened the door, quickly went in the room, smashed all the glass windows in the room, and then quickly left. So he did all that in the 30 seconds or whatever he could go without taking another breath. He knew not to breathe the air in there. And he knew also just not to call whatever the equivalent of 911 was at the time, because if all the emergency people just ran into the lab, they could succumb to the same fate as him. They could breathe the same gas and end up with the same issue. So that's how he died. I don't know, some people thought it was suicide, but like, I don't know, that's kind of elaborate, I think. And not only that, but it's putting a lot of other people in danger too. His graduate student, by the way, that guy that found him became a famous photochemist named Michael Kasha. So there's a Kasha rule as well. It's not a law, it's just a rule. But anyway, fun facts in chemical history, I guess. So this is a picture of the periodic table, updated from the original Mendeleev one, because you can see there's a row at the right with all the noble gases. Mendeleev didn't know those existed, so this had to be added later on. What we find is that these covalent bonds, the number of covalent bonds a given element can make is very characteristic of the element. We know there's a bunch that will only make one bond, like hydrogen, fluorine, chlorine, bromine, iodine. They only have enough, their electrons are such that they like to make a single bond in most typical cases. Few of those can make more in some cases, but most of the time they like to make one. Oxygen likes to make two, nitrogen likes to make three, carbon likes to make four, and these are sort of facts that people observed after characterizing many, many compounds. So this is just a molecular modeling kit, and you may have played with one of these before. Basically, the little balls are colored different colors with some specific number of holes, and the number of holes generally corresponds to the number of bonds that element of that type can make. So if you had the little white one there, it's a hydrogen, it only has a single hole in it. The black one is a carbon, it has 4 holes, so it'll make 4. And you make molecules then by using sticks to represent the covalent bonds. And as long as all the holes are filled, you'll have a stable molecule. And so you can actually use this very simple model to predict what structures could be stable and could be actual real molecules and what ones are not reasonable. Because if there's any holes that are unfilled, or if there's any, well, I guess you can't make more bonds than the number of holes, so I guess that answers that part of it too. That's a bit maybe of an oversimplification. There's certainly lots of very weird and interesting things that happen in chemical bonding, but many, many, many molecules can be described very simply using this kind of a manual kind of model you can hold in your hand. So what's actually interesting is if you look at the number of bonds that something can make, it's dictated by its position in the periodic table. That if you look over here on the periodic table, that first whole row, which are the noble gases, they all make 0 bonds. The next line over, which are, we call those the halogens, they all make 1 covalent bond. The next ones, which are called chalcogens, which you may have never heard that word before, they make 2, 3, which would be nitrogen and phosphorus, which are called pnictogens. And then, I don't know what the name for carbon is for 4. All the ones in this row like to make 4. And you can see the elements here that are in yellow and in green. We call them nonmetals or metalloids. The nonmetals are the ones that will form these covalent bonds. These are the ones that make molecules. These are the ones you commonly find in organic chemistry. All the other ones are metals, and metals, not to say they can't form covalent bonds, but that's not their typical form of bonding. They do other things like form what's called ionic bonds or metallic bonds. The ones that are up the middle, the green ones, are kind of straddling the line between the metals and the nonmetals. These ones have properties that are kind of like metals, but kind of also not like metals. So an example, one property of metals is that they conduct electricity really well. The yellow ones do not conduct electricity very well. We would call these insulators. And the ones that are in the middle, the green ones, we would call semiconductors. They can conduct electricity a bit, not as good as metals, but not as bad as the insulators. So yeah, the blue ones, we would make wires out of them. The yellow ones we would use to make the casing around the wires so you can hold the wire and not get electrocuted. So this is actually very interesting when people realize that the number of bonds matches with their periodic table position, because at the time, Mendeleev never heard of bonds. He didn't know what a covalent bond was. They didn't really understand the structure of molecules very well. He didn't use this to arrange them. He used their weights and the properties of the pure elements themselves. So people kind of realized, I guess, when this came around, that they were really onto something with the way the periodic table was arranged. So carbon likes to make 4 bonds. All the common molecules you're probably aware of that contain carbon have 4 bonds. Like CO2, you can see it has 2 oxygens, but it makes what's called a double bond to each one of these oxygens for a total of 4. Methane, CH4, it's also called natural gas, has 4 bonds, individual bonds to carbon. The bottom right one, it's a chlorofluorocarbon, which are also called freons, which we're going to talk about in a later unit. And the top right one is acetylene, which are used in, as a fuel for like acetylene torches, burns very hot. It has a carbon-carbon triple bond, so you can have single, double, and triple bonds. As long as the total adds up to 4, carbon is happy. Great. It is possible to be outside this normal number of bonds, and the example I'm going to give you here is ozone. Ozone, the preferred structure for ozone is drawn underneath there on the right. Ozone is just a molecule that has 3 oxygen atoms bound together. It has an oxygen with 3 bonds in the center, and that makes this molecule much more reactive. So if you're outside that normal number of bonds, as you would predict based on the position of the element in the periodic table, it's generally going to be a more reactive molecule. So you can have carbon that has only 3 bonds, but that's going to be a much more reactive carbon. Okay, it might only last for milliseconds. So yeah, these are guidelines, maybe not hard, fast rules. Okay, a few more questions here. A chemical bond that is formed by the sharing of an electron pair between 2 atoms is called what? A metallic bond, a covalent bond, a War bond, or an ionic bond? So yeah, this is covalent. B. How many bonds does carbon typically make to other elements? 1, 2, 3, or 4? Well, you can just look at its position in the periodic table and look at it and see, yeah, it makes 4. And you know anything in the nitrogen line, like nitrogen or phosphorus, will make 3 typically. Fluorine, chlorine, bromine, iodine make 1 because of its position on the periodic table as well, without getting into exceptions. All right, carbon dioxide is next down the line. We did oxygen, nitrogen, argon, then we get to CO2, which is present in very small amounts relative to the other gases, but is very important for life on Earth. 0.04%. That number is slowly rising as well. Now, the air we breathe in, actually, I used to wonder if somebody like collapses and you're giving them mouth to mouth, if you're breathing out air, how's that going to help them? Aren't you extracting the oxygen out every time you breathe? I don't even know if mouth to mouth is the way they recommend you do it anymore, or if it's just chest compressions. I don't know. God help you guys if someone collapses here, but and you expect me to do something about it. But what you can see here is that inhaled air is about 21% oxygen. Exhaled air is more like 16%. So we take out maybe a quarter of the oxygen in every breath that we breathe in and breathe out. We don't take all of it. So even the air we're breathing out has a significant amount of oxygen in it. Which I guess also makes sense, because if you're like starting a fire in a fireplace, often what you do is you'll blow on the coals to try to make fan the flames a little bit to get it started. If you're blowing air that had no oxygen, that wouldn't do anything, that wouldn't help. So I guess it's that 16% is enough. Notice the carbon dioxide goes up from 0.04 to 4%. So basically everything you can think of it kind of like this. Every breath that you take in, around 5% of that volume goes back out as CO2, 4%, I guess. So every breathe in, oxygen goes in, breathe out, oxygen goes back out with a carbon atom. So that's why, remember, when you lose weight, or just not even losing weight, just when you burn your sugars and fats or whatever in your diet, that's how it comes out. Now units, we're using percentages, and that's great for things that are like 70% or 20%, big numbers like that. It gets awkward though when you're like CO2 level or below, like 0.04%. And then if you looked at like helium, it's like 0.0000001%. Like for gases that are present in small amounts, we generally don't use percent because you get these super small numbers. What we often use is something called parts per million or parts per billion, or maybe in some cases parts per trillion. So a percent, you can think of a percent basically just being parts per 100. 1% is 1 part in 100. So parts per 1,000, 10 parts per 1,000 is equal to 1 part per 100. So if CO2, and this number is old now, this was like from a couple of years ago, we've put more CO2 into the air since then, 0.0385%, that means for every 100 parts air, 0.0385 parts of that is CO2. So what we might want to use instead of these very small numbers is a different unit, which is in units of parts per million. And to do this, basically we just have to multiply by 10 to the power of 4, or 10,000. So 0.0385% CO2 is the same thing as saying 385 parts per million. And if you had very small numbers even at that level, you could go to parts per billion or parts per trillion. Okay, so what we're going to be doing is moving away from these 4 gases, as fun and important as they are, and we're going to look at all of the other gases that are present in air, even though they amount to very, very small percentages relative to those 4 that we just talked about. Because it doesn't have to be present in a very high amount to be extremely relevant to us, right? And so these are just some examples. Every time you smell something, that's a gas phase molecule that you are coming into contact with. And some of these things smell very good, some of these things do not smell very good, but we can recognize their presence because of gas phase molecules that these things are giving off. And we can often detect extremely low concentrations of all of these gases in our air. And human beings actually, compared to many animals, aren't specifically, aren't that great smellers, Other animals like dogs and bears and other things are much better, which is good. I have a cat at home. It's not very old, only like 4 years old, and the cat's like pretty well blind. And went to the vet and everything, and just nothing really you can do. It's not like an infection or something. It's just bad genes, I guess. And it's actually kind of sad. Like, he's got all these paths around the house that he can walk, and if you put like a box in the way of one of his paths, he'll just like blunder into the box because like he doesn't see it. He just will walk right into it. He can kind of see like a little bit, but yeah, not great. He has these treats he really likes, and if you spill the treats out on the floor, he has to like smell around for them. He can't see them. And so every once in a while you give him a few, and then you'll find he missed 1 or 2, so he can't find them. Or he'll like root around for like 30 seconds trying to find where you put them on the floor, and then eventually he gets them. But anyway, why I'm talking about my cat is his sense of smell is still great. And for many animals, being blind is probably not as bad a handicap as not being able to smell. Because that's one of the primary ways that animals like cats and dogs interact with their environment, much more so than human beings. Like, I kind of feel like if I had to give up one of my senses, smell would probably be the first one to go. Maybe taste. Maybe taste. I guess taste, the benefit there is you probably wouldn't care if you're eating healthy food or gross food anymore. Gross food, like, if you can't taste it, then you might as well just eat healthy stuff. But I think as a chemist, it's maybe more important for me to have a good sense of smell than most people, because if I find myself in a very dangerous situation in the lab, it would be good for me to know that that's the case. So yeah, maybe for people like me, it's important that I do not lose my sense of smell if I want to stay alive. So yeah. We had a person working in our apartment a few years ago who lost his sense of smell, and he was doing a chemical reaction that blew up in his face, basically, and he inhaled it, and he was fine, and there's no visible scars or trauma or anything like that, but he lost his sense of smell. And he lived in a house with like dozens of cats, so it was probably a good thing that he couldn't smell anything, because, you know, cats aren't that smelly, but if you put a lot of them in one space, no matter what you do, I think you're a little bit stuck. All right, so where we're going with this, in terms of pollutants, is we're going to be looking at a number of very specific pollutants, 6 of them that are listed here. There's maybe 1 or 2 extras we'll tack on at the end. These are important because these are all ones that are sort of target regulated pollutants in our air, as indicated by Environment Canada. These are sort of the target, the most important tropospheric pollutants that maybe we're at highest risk of causing negative health effects in our generalized environment. We're not going to talk about these very much today. I think we're about to finish. But one thing that's very nice is since these started to be regulated, things have gotten dramatically better. And one thing that hopefully you'll see as we get deeper into this presentation is you are probably in the best place in the world right now, if you're in Wolfville, in terms of breathing air quality. Okay, so that's a very, very good thing about where we live right now and the time we live in right now, because if you went back to the 1970s, that may not have been the case. And now I'm saying that, but I live in Port Williams, which sometimes you get some interesting farm smells. Maybe in cases like that, maybe there is cleaner air, but most of the time, it smells great where I live. All right, thank you very much, everybody. If you have any questions, you can email me, I suppose, put them in the chat, or we can address them when we come back. We don't have class next Tuesday. Tuesday's a break, so I guess it's a full week before we see each other again. And before we do see each other again in a week, don't forget that you need to have submitted already your assignment 1. Any questions about that, email me, but 1-page PDF or Word document. Thank you very much, and we'll see you next week.